Hello everyone, welcome to this video. Let's look at our next question here. This question says if P and Q are two distinct primes, right? And we suppose that H is a proper subset of integers, right? And which is a group under addition, right? So they are saying H is a proper subset of Z, which is is a group under addition, right? And it contains exactly 3 elements of this set. Now this set is given to us. Let's call this set by the name S, right? So they are saying H would be containing only 3 elements and exactly 3 elements of this set, right? So moreover, we need to show this thing, and we need to determine which of these 5 elements are exactly present in H, right? So we have these 5 as our options. So let's proceed by solving the question. We will use all the information. What information we have with us? We have the information that P and Q are distinct primes. This is the first information. Second is H is a proper subset of the group of integers. This is the second information. We know a group of integers is a group under addition, right? It is a cyclic group, and moreover we are given this set, correct? So we know that the set of integers under addition, that is a cyclic group and having infinite order, right? And we know that every subgroup of a cyclic group is also cyclic, hence H would also be cyclic. Moreover, we know because Z is in infinite set, right, it would have only 2 generators. All of these things we have already studied in detail in the group theory when we were discussing the concept. So if one is not able to recall what are those, they can go back to the theory part and then you can come back here, right? Okay, so when Z is infinite, so they would have only 2 generators, which is +1 and -1. We all know that, right? Moreover, we are saying H is a subgroup of Z, so it is also cyclic. However, its generators, they cannot be the members 1 and -1. Either of them, they cannot be the generators of H. Why? Because if we take any one of them to be the generator of this subgroup H, right, in that case it would generate the whole set, which is that of integers. However, because H is a proper subset of the set of integers, therefore the intersection of its complement with it is empty. They are disjoint with each other, hence we cannot take 1 and -1 as their generators, correct? So let's take any prime number to be its generator. In particular, let's take this particular P as its generator, right? Now because it is an additive group, so we would have all the elements like this within this group, correct, and so on. So basically what would be your nth element? It would be P plus P plus P up to so on. How many times? In total n times, correct? So we can write that it would contain elements of this kind Pn, where this n is some integer, right? So this is how we can represent our given subgroup. Now, as I've already told you, the given set, we have named this to be S. Now from this set, we need to knock off 2 elements. There are 5 elements present within it. We need to knock off 2 elements from it such that we are left with exactly 3, which are the members of H. So let's see how we can proceed here. You can simply see this P plus Q cannot be present in H. We will eliminate this one. But why? It is because all the elements of H are of this form Pn, correct? So we cannot have in any case some element of this kind P plus Q, because Q is some other prime which cannot be formed from P, right? Because the GCD of P and Q, that is given to be 1, because they are distinct, right? So they do not have anything in common. So we cannot write Q as some n into P, where n is some integer. So therefore P plus Q would surely be not present in this particular set H, correct? Now we are left with 4 choices here. We need to see what choice we can eliminate here in our particular case, right? So out of these 4 choices, we can have these 3 options, which are P, PQ and P raised to power Q, first 3, then P, last 2, right? And then these P, PQ and Q raised to power P. We can have more choices as well, but P would surely be present with us because we are taking this to be the generator here, correct? So let's see what do we have here. So because we are given P and Q as distinct primes, so as I've told you that GCD is 1, so it would suggest that because their GCD is 1, so P will not divide anything except P or its powers. So it would not it will not divide both of them together, either P raised to power Q and Q raised to power P, right? And moreover, it would not divide anything which do not contain P. So it would obviously not divide Q raised to power P by the definition of this prime number. So therefore, we can very easily eliminate this Q raised to power P, and hence we will be left with only the elements P, PQ and P raised to power Q of S. So hence our H would be nothing but these containing these three elements. So I hope you understood this question well. Well, that is it for this video. Thank you for watching.